Okay, we are on. So we are continuing with our introduction to transport phenomena. So I'm going to briefly go to the part that we left off yesterday. That was this one. So essentially we had the last thing we did, we had a quick discussion on how would you tackle solving this flow. There are multiple ways we can approach this problem. One is simply to do sort of a force balance, which is kind of a macroscopic way to look at things to larger system. You can do force balance on any size and any scale. And another one would be actually to have details of the flow through this tube, which would allow us to get both velocity and shear stresses, and then you can integrate the shear stresses and actually get the forcing that this fluid exerts on the tube. And we're going to kind of go back and forth between both cases. So pipe is one of the most common geometries that we encounter. Even when we don't have pipe, we kind of simplify and think that we do. So let's just kind of survey all the range and sizes of pipes that appear in the industry. So transport, the largest ones are the ones that we transport oil in. This is an example of Alaskan pipeline, which is huge. I mean, if I was at some point standing next to it, and let's say that my height would be up to here. So that's a very large pipe that we transport, and this example shows the network of pipes that is slightly outdated, but for the purposes of this presentation is just fine. So essentially, we typically have not just one pipe, but a network of pipes. You can imagine the very small scale on the other side of the spectrum, inside the porous rock, also is a network of pipes. So if you zoom in any rock that you pass by, if you take a core sample, which we often do, if you zoom in with X-ray, you need X-ray vision for this. This is approximately 2 millimeters of rock. Okay? Then I can see a number of grains. Grain size in sandstone typically goes on the order of 100 to 400 micrometers. Okay? So you can see individual grains, and what's left in between is the pore spaces that we're flowing through. So this is a sandstone, this is the pore space, and your fluid is moving through. It could be one fluid, it could be multiple. This is often in this is going on in 3 dimensions, so you can simplify this space into a network of pipes as well. So those are micron scale pipes. Now near Velbor itself is a pipe, or annulus, depending on which part. Right? And then we're connecting, there's fractures connecting to it, and then we have the porous medium, which is neighboring here. You might have inside the fracture porous medium as well, which is propant, fracture. So fractures we will often, and then there might be some natural fractures connected to it and their networks. So those geometries, so I mentioned annulus, and fractures are often visualized as slits. So tube, annulus, and slit, and flow around the sphere. If you imagine that grain is a sphere, or propant is a sphere, especially the one that is manufactured. So often those are the most common geometries that we're going to be dealing with. So most of the problems we're going to solve in those 4 geometries. If you actually imagine fluids, now this is multiple fluids situation. We're not going to go into multiple fluids for the most part in this course because it's really fundamental. But later on, you will get courses that will introduce multiple fluids. So this is just to visualize. This is a sphere pack. And this is basically you have curved interface between air and water inside of a sphere packing. And one is displacing each other. And the whole point for a lot of people in this building is to enhance the oil recovery. So basically once you have residual fluid, if the wetting fluid kind of surrounds oil and snaps it off and traps it as a blob, you're trying to get that blob out with all enhanced methods. And here we actually have air. This was actually accident. Air got into the system, oil and water inside of a polyethylene, which is an oil wet core. Okay. So we're not gonna get into the, and then the smallest pipes we're dealing with so far is the shales and mudrocks. There's a lot of research going on in this department and many others. They're very fine-grained rocks. So if the siliciclastic component has grains of size of 1 micron and less, okay? But then there's a lot of clays and organic content mixed in, and that results in a very complex pore system. So you can see organic matter pores, as well as some sort of kind of slit-like pores around the silt grains. So this is, the scale bar here is 2 microns. So this is 2 microns, and I can see about 10 pores across. Okay. So this is nanometer scale. Okay. These are the pores inside the organic matter. So if I think about those as pores or tubes, they're really not tubes. They're more like inside of spheres because they're from a gas bubbling inside this matter. So essentially, you can find them in the range of 5 to 750 nanometers, nano being 10 to the minus 9. So those are the smallest pipes. And we will see different types of transport. Typically, if you have momentum transport or pressure difference driven flow, that's typically dominant, except in these, where basically diffusion starts competing. Diffusion is typically on the time scales that are way less, that you need more time for. So if it's not dominant, you're not going to look at it. But in these, actually, diffusion becomes competitive with the momentum transfer because of the size of the pores. So these are the things that you need to think about when you're solving problems. In this course, we're going to really focus on kind of fundamental solution of the problems. But once you're applying these methods that we're going to learn, you really have to figure out, okay, well, what is the dominant type of transport that I need to focus? Let me isolate one, okay, and work with that first and get some basic idea about your problem and then move on to more complex things. All right. So the three scales at which classical transport phenomena are studied are macroscopic, microscopic, and molecular. Beware of the words macro and micro. They're always relative to the area you're in. So whenever actually somebody starts a discussion, say, can you define these for me, please? What do you mean by macro? What is macro for you? What is micro for you? Okay. So in this case, what I mean by continuum or macroscopic scale, it's the one that is larger than a centimeter. So there is a space and time continuum in terms of what we're seeing. Then microscopic would be micron to centimeter scale, and then below that we have molecular, atomic, or atomic scale. And this is actually what is kind of shown on the textbook. I didn't bring textbook yesterday. Mine is a very old version. It's also kind of falling apart from the use. But the version, the date, or the state of the book doesn't matter as long as it's serving your purpose. There's also a version that is in the 2 different colors, sort of like dark red and yellow. And then their international edition will be all red, all the same. Okay? But the sketch here is basically showing these 3 scales. So to jump the scales, I have to assume that I have enough or representativeness that I can average this scale and move on and look into the property. Okay. So we will be looking into molecular scale only for a limited amount of time, and that's going to be to explain viscosity from a very fundamental theoretical point. And that's just to illuminate how it can be useful to look at things that way. Most of the time, we're going to be on the continuum scale. Okay. All right. So our key assumption is the continuum of space and time, even though we know that matter is composed of molecules, and they're the ones that are actually the agents of transport. But we will try to look and define properties that kind of put us away from looking at individual molecules. So if I have momentum transport, or most of the types of transport, they're really from molecular collisions. But I don't want to think about molecular collisions context of a well-bore, that's way too small a scale. So this is how we average properties and jump to the scale above. In many applications, this is just fine, and we can successfully solve many problems assuming matter as a continuum. It's actually that shell that I showed that actually where those assumptions start to break. If you're on a nanometer scale size of a pores, you're often 10 to 20 times larger than a molecule that you're looking into. If you're looking at a gas molecule, there are 3 angstroms, and if you're in 3 nanometers, that's 10 to 1, right? So that's where basically your assumptions of continuum start to break down. So whatever simulation that you're using with the continuum assumptions starts to get wrong and starts to deviate from what reality actually is. So that's something to think about. Nevertheless, we learn a lot from these continuum assumptions anyway. So we build across scales by coming up with and confirming laws. And when I say coming up with, I literally mean guess. And I'm actually going to attempt to play a video here, though I hope it's connected properly. I might not have audio here. Not sure what is needed.
How we would look for new law.
Oh.
In general, we look for new law by the following.
You hear things, you don't see things. Interesting. Just a moment. So this is Richard Feynman. Does everyone know who Richard Feynman is? Famous physicist. And I like how we're just going to play 2 minutes of it, of how do you actually come up with laws and what is the scientific procedure.
We look for new law by the following process. First, we guess it. Then we that's the really true. Then we compute the consequences of the guess to see what, if this is right, if this law that we guess is right, we see what it would imply. And then we compare those computation results to nature, or we say compared to experiment or experience, compare it directly with observation to see if it works. If it disagrees with experiment, it's wrong. And that simple statement is the key to science. It doesn't make a difference how beautiful your guess is, it doesn't make a difference how smart you are who made the guess, or what his name is. If it disagrees with experiment, it's wrong. That's all there is to it. It's therefore not unscientific to take a guess, although many people who are not in science think it is. For instance, I had a conversation about flying saucers some years ago with laymen. Because I'm scientific, I know all about flying saucers. So I said, I don't think there are flying saucers. So my antagonist said, is it impossible that there are flying saucers? Can you prove that it's impossible? I said, no, I can't prove it's impossible. It's just very unlikely. That, they say, you are very unscientific. If you can't prove it impossible, then how can you say it's likely that it's unlikely? So that's the way, that is scientific. It is scientific only to say what's more likely and less likely, and not to be proving all the time possible and impossible. To define what I mean, I finally said to him, listen, I mean that from my knowledge of the world that I feel around me, I think that it is much more likely that the reports of flying saucers are the result of the known irrational characteristics of terrestrial intelligence rather than the unknown rational efforts of extraterrestrial intelligence. It's just more likely, that's it. And it's a good guess. And we always try to guess the most likely explanation, keeping in the back of the mind the fact that if it doesn't work, then we must discuss the other possibilities. There was, for instance, for a while.
So I'm going to stop it here just for a couple of minutes to play this. Just the point that is made here is that you do indeed guess, or you have some sort of intuitive guess about how things proceed. Those are the laws, typically, that we often accept. Darcy's law is one such example that we always operate with in porous media. But it is just a law. Fundamentally, it's not proven true. It has its limitations. It works sometimes, assuming certain assumptions, and it doesn't work in other cases. Okay? So you always kind of come up with laws, and these laws are what enables you to kind of jump across the scales, because these laws will use some average quantities from smaller scale that you can actually measure. Okay? So it relates to the experience we have. And it can also change as you change. So often it's extremely hard to break down the accepted laws, but new situations might bring new challenges where those laws don't apply anymore. So you always have to keep an open mind. So what we are going to postulate here, what is going on here? Just a second, the view is strange. What we are going to postulate again,
I think if you go on the top, it says swap.
Yes, but I don't see that on mine. That's the problem. So it's swapped. So now it did swap it. But let's see if I can do it here. All right, swap. No. Oh wow.
Can you just move your mouse for a second?
Okay. I think I need to try. Apologies. Why I try to swap is then what's on my screen is what's captured on the video. Then on the video you had this weird sort of sequence, and I tried to swap that, and I got them swapped, but I can't. Let's try system preferences, displays. It's mirrored. Let's try without mirroring. Does that work? No, still the same. All right, well, we'll work with this for now. And then I'll play with it later. So we're gonna assume mass, momentum, and energy conservation. And that's basically a postulate, and you build from there. It's these conservation equations. They result from applying conservation laws on small scale, and those are the ones that we're ultimately solving. And the beauty of math, though math is not equivalent to physics, and I'm not going to play another Fineman video on differences in math and physics, but math in itself works with abstractions. So it's trying to be more general, and whatever it talks about doesn't necessarily have to be rooted in reality. If you're an engineer, you are actually rooted in reality, and you want to link everything to the observations that you have and measurements that you have, which is why Fineman says, if experiment doesn't agree, your model is wrong. Okay? Because you're trying to model that experiment and whatever it is that you're seeing. Whereas math is like, well, I'm correct in some other universe. Okay? It doesn't really matter. So in that sense, that said, the tool, or the mathematics as a tool to solve these equations, is very similar whether you're conserving mass, whether you're conserving heat or energy, or whether you're conserving momentum. So there are certain tools that we can apply in all of those cases that are kind of parallel. And that's what we're kind of be exploring in this course by looking at all three types of transports at the same time. So you will notice the similarity on the syllabus. We will start with microscopic momentum transport, molecular basis for viscosity. This is the time where we're going to be looking into molecular part and kind of understand how viscosity as a measurement builds up from molecular scale. And then we're going to leave it behind. Okay? We're going to build that understanding, and then we're going to jump to continuum scale and work with shell balances and derive equations of change that we're going to solve. There will be two different ways to solve. Shell balances is used typically for steady state solutions, and we're going to use it as a tool for solving steady state problems. But similar balance can be done in time as well, and that results in more general equations of change. Equations of change are more general, but overall, when you have a very general equation that has all of the possible terms you could have, and you start solving it, it takes you one page to bring it down to your own little system. So shell balances are often more intuitive and visual than these most general equations of change are. So they're general, but that's also a problem. Okay? So sometimes it's hard to see how to solve them because of that. And you will be allowed to, in the problems that you work on, unless I specifically say use one or the other, you will be allowed to pick whatever works best for you. And then we will work with non-Newtonian fluid flows as well. So most of the time we will be working with Newtonian, but we will have a non-Newtonian fluid section as well. And then we will move on to porous media applications and some microscopic momentum transport. And in this scale of this textbook, micro is taken again at this scale of the individual pipes. That is definitely larger than a millimeter or centimeter in our applications. And then macroscopic means sort of a larger system. Okay? So in that sense, we're going to look at those balances as well. Still the same conservation laws apply. And we will move on then to heat transport and mass transport. And we will again repeat the sequence. We will look into the molecular basis for it, shell balances and equations of change, and then we'll repeat the sequence for mass transport. Okay, and those are those similarities that I was talking about. Then we will sometimes spend some time on time-dependent problems for all three types of transport. Okay? And equations we're solving in this case will be basically the same, it's just how do we interpret them physically. And finally, we will conclude with dimensional analysis. For those of you who have taken, is anybody here sitting from the previous time I taught this? So I'm skipping, you will be glad to know that we're killing vorticity and streamline solutions for flow around the sphere. So that has proven to be the most egregious and time-consuming solving process. Essentially proving the equations and then starting with the first problem took about 2 weeks, right?
Yeah.
Things out.
That was really hard.
So that was a killer. And I can measure it for you using my YouTube videos. So I went to review because I was discussing it myself. I've been using it and teaching it for years, and I was like, okay, maybe I should finally drop it. And I go to look over the videos just to see how much time it took, because that's why we have time for dimensional analysis. And normally, my single YouTube video has about 20 to 40 views, which means each student looked at it once or twice, right? Clicked on it twice at least, as far as YouTube knows. My vorticity, 2,000. so it wasn't going well. So I was like, yeah, this might be a proof that I need to just let it go. So I'm finally, I love the theory, it's beautiful. It takes just forever to actually solve for flow around the sphere. To get that analytical solution, you need the method of streamlines. And building that knowledge just takes a moment, and it's a lot of solution. So we ultimately took that flow around the sphere and actually managed to get to permeability for a sphere pack. There was like a beautiful exercise in upscaling there, which is why I was hanging on to that problem for so long. But I was like, okay, maybe I just need to drop it because students don't like it. So if you do want to learn it, it's on YouTube. So you can be a student 2001 watching it over there. So have fun. So let's go back to key observations that we had before. So when do we have motions? So through all of these tubes and geometries that we're interested in, when do I have motion? So my motion occurs whenever there is a gradient of some potential, for instance, pressure. Okay. This is our first opportunity to postulate a law. Okay. So basically I have some flux, something, and I'm trying to, my particles will move to try to equilibrate that flux, okay, and counter it. So what is the simplest law that I could come up with that tells me how flux of particles reacts to this gradient of potential, whatever this potential may be. So fluid flux as opposed to, as a function of gradient in pressure. What's the simplest law you could come up with? Mathematically, what would that function be? Laws that we like are always linear. Linear function. Simplest change, right? F of x is ax plus b. We don't even have that b. So f of x is ax. And my coefficient a changes depending on the presentation, on whatever it is that I'm looking at. If I have a lab, I go measure a bunch of things, and I figure out what a fits this relationship the best. And it gives me my coefficient of proportionality. So that a, in Darcy's law, where flux q, and you have gradient of p, is permeability over viscosity, right? And that's what Darcy did. He was flowing water through sand packs, and he realized that there's a very nice and linear relationship between the flux of water that he literally measured with a bucket, okay, and the gradient of potential, which was the gradient of rho GH. So gradient of rho GH. So therefore, those are the simplest laws we come up with. And then we work with them. We have to know when do they work, when do they don't. So they're not necessarily true or not true. They're not proved in a strong sense all of the time. But we work with them, and they give us very good first order approximations. Okay. Now, just before I end this introduction, we will have probably one or two computational methods, as I said. So this course is not really about computation. Whatever we do is computation. You're going to get kind of a recipe book of what to do and how to solve things. So this is not a computational course by any means. However, it is useful if you build a computational tool that will help you in all of your courses for quickly plotting something, for quickly. MATLAB is one of those tools. I'm not actually advertising, oh, you gotta use MATLAB. There are a lot of alternatives. But if you don't have a tool like that already, find one. Okay? It's gonna help you. It's gonna extend your ability to solve problems. And you being fluent in it means that you're not gonna have that delay in actually solving something. You're just gonna get on a machine and quickly type it up and get it over with. So in that sense, if you want to, there is resources, just like a basic review of how to use MATLAB. And MATLAB is free for UT students. Whatever is true for MATLAB is also true for its free variety Octave. In itself, why not Python or some other programming language? Why not? You can. Doesn't matter. Okay. So you can pick whatever it is. Actually, in undergraduate course that I'm teaching, that used to be a MATLAB course in this department, which was Introduction of Numerical Methods with MATLAB. We're switching this year to Python. So in that sense, the choice is not necessarily up to you. What I'm telling you is go find yourself a tool that will help you as you go through the course. What its name is, it doesn't really matter. But for MATLAB and Python, for both, there's plenty of resources out there. Compiled languages like C, C++, and Fortran are cooler in what they can do, but they're also much more involved, so there's a much steeper curve in learning them. So I wouldn't call them quick. Okay? You don't get results quickly. MATLAB and Python are both interpreted, so you can literally type things into a command line and get the result. You don't have to compile anything before. So that's just a suggestion. And for first reading, if you just go to the initial chapter in the textbook, it's actually a fun little development of momentum transfer from just like rigid body perspective. And these are just the reading that refers to the plots that I was showing at the very beginning of this introductory lecture. If you need sort of a colorful introduction on importance of oil and natural gas, you can go to this book by SPE, and the website that has a lot of information on energy use is listed here as well. Okay, so this is our introduction, and I will continue with 20 minutes of basically switching to our viscosity discussion. I will post this after. I will post this up. So I did not post this lecture just yet. So this is going to be our starting point in microscopic momentum transport. So this is the session on momentum transport. So first we will, basically we're gonna pretty much cover chapter 1 in Bird, Stewart, and Lightfoot. Okay? We're not gonna necessarily cover it in order, and I have reason for that. But basically entire chapter is relevant. And what we're going to do is we're going to define viscosity and Newtonian fluids, as well as what sets them apart from the rest, and explain molecular basis for viscosity for gases and liquids. We're going to also quickly review, this is going to be a very brief review of the estimate of viscosity of complex fluids, because we do have a lot of complex fluids in petroleum engineering. And then we're also going to define this mathematical toolbox that uses tensors and tensor analysis to look at the momentum transfer. And also we're going to do that in different coordinate systems. Our Cartesian coordinate system is wonderful, orthogonal, all of the directions are orthogonal to each other. And wherever I go, my basic element of my coordinate system is the same, it's just translated. The only problem is that most of the systems we work with are cylinders, right? And cylindrical, you're going to have the basic problem that your element, when you basically look at the basic A in cylinder, if you look at the radial coordinate that is pointing outward, it's changing direction as you're going around the radius, right? So your coordinate system is not the same, or your coordinate vectors are not the same at every point. Also, the size of the basic element that you're dealing with in this coordinate, like a little cylindrical shell, okay, that also changes size as you're going more outward. Okay? And that creates a little trouble. Okay? So that's why but we will have to go and switch between different coordinate systems. It's still orthogonal coordinate system, meaning that all of the directions are always orthogonal to each other. And then the even more complex one that has the most curvature is the one that is spherical. So we will have to kind of go switching back and forth between different systems. Specifically, we're going to get well versed in the cylindrical coordinate system. All right. So if you have two parallel plates, okay, you can take that just to wake yourself up if it's too late in the afternoon. Draw two lines, and please draw, if I have Newtonian fluid in between two thin plates, one is stationary, the one on top, and the other is moving at constant velocity, that's the one on the bottom, and I'm calling that velocity Vx. Okay? How does a steady state velocity profile? So I let it develop at initial time, and then I wait for time long enough until this velocity profile stops changing. How does it look like? This was a quiz. So, solution is visible. But I hope some of you still didn't see it, so it still worked. Okay, it was right there. So basically, this velocity profile is simple change, the linear change between sitting still and moving, right? Especially since the bottom plate is constant. So basically, I have this linear velocity profile between two plates. So it's basically Isaac Newton that analyzed this the first. And we are assuming laminar flow regime, so I have a relatively small system, small distances. So if I look at the plate area, and I'm going to call this x direction and y direction. Yeah. Basically, he looked at, okay, so if I'm analyzing this problem, I'm going to simply, this is the simplest case of basically having only one velocity that is non-zero. All other y and z are 0. So I do have x direction velocity, but what is the direction of the transfer of momentum that happens? So my bottom plate has momentum, right? It's mass times v. And that's obviously transferred, but in which direction?
Why?
Why? So I have something moving on the bottom, and eventually all of the things kind of get moving with it. Okay? But those things are basically layers in y. That's the kind of the key complexity especially once you go into 3D, you need to go to tensors to describe that. But for now, we're just going to look at that simple case. So basically, if I'm looking at the shear force, and shear force is literally this force in direction parallel to those plates, it's proportional to the velocity that I'm moving the lower plate with, obviously. The larger the separation, the smaller the force, so it's inversely proportional to that. And it's also proportional to the area that I have. So when I actually formalize that, I'm going to call shear stress tau yx as F divided by A. And this is my sign, this yx is the sign that my transfer of momentum is orthogonal to the actual velocity direction. So velocity direction is x, but the momentum transfer is in y. And those two things are orthogonal. And this proportionality constant is called mu. So this is my linear law. Okay? I'm normalizing my force per area because the plate could come in various sizes. So that's my shear stress. And that is proportional, okay, to velocity difference. It was a 0 one, so we didn't look at it initially. But it's really velocity difference and by the spacing between the two. Okay? Now, basically what I have is Vx of y is actually 0, so I'm going to have a 0 minus Vx divided by y, which is my minus, comes from that. Okay. And that minus in any kind of laws of this nature is there because of the coordinate systems. Our transfer of momentum always goes from area of more to area of less. Yes? Whatever it is that I'm transferring, I'm always transferring from wherever I have more of it to wherever I have less of it. However, whichever coordinate system we have, it's always pointing from less to more. My positively oriented vectors in any coordinate system go from 0 to, right, more. So that's why we always have minus in there. Whenever you have kind of transfer of this sort of a physical quantity. So that's why minus will always show up. So this is my momentum flux per unit area and per unit time as well, because I'm looking at the velocity. So again, direction of the force exerted by this, what we call, so this momentum transfer, if I divide my plate areas into two regions, the bottom and the top. Okay? What I, in my coordinate system, call my lesser y region. The greater y region is the one that is red. Okay? So the direction of the transfer is from lesser y to greater y. Okay? So that is the direction of the momentum transfer, which is, however, the force itself is actually shear force. Okay? And that's literally what plate feels. Okay? And that force direction is actually in the x direction. Okay? So that's something important to understand. So this flux tau yx is also the force that is in x direction that is exerted by this portion, the lesser y portion of the fluid, on the top portion of the fluid. So I can have these two views. One view is the momentum transfer view, okay? And the other view is this force view. Okay? So I can look at it as momentum transfer of the particles from at the bottom moving up. Okay? Or I can simply look at the force that this is exerted across this area, or this lesser portion. And force is in y direction, in x direction, and my momentum transfer is in y direction. So both perspectives are useful for different types of problems. Okay? So we will go till another 5 or 10 minutes or so to replace the regular 15-minute class. Okay? All right. So again, we have this, I explained this already, the momentum perspective. And this momentum perspective is helpful. So force perspective is helpful from what we kind of observe or feel on larger scale or in the lab. Whereas the momentum perspective is useful from seeing how things happen actually on molecular scale. So it's the molecules on the bottom that simply have more momentum, which is m times velocity, those that are closer to the plate that is moving. And in the momentum transfer, as they're moving around, okay, that will get transported to the area where there's less of it, which is the top. Okay. So that's actually happening because of the molecular movement and molecular collisions. And that's happening in y directions. So you can also look at the neighboring layers of fluid. So neighboring layers of fluid have this different velocity that is then transferring up. Okay. And you can look at it also if you so right now we're just, if you want to actually look at it as a momentum transfer, so right now we were looking at just velocity, okay? But momentum is really mass times velocity, or if I'm looking at the continuum, I'm going to look at the density times velocity. So you can divide by density and multiply by density. We're assuming constant density, so it doesn't matter. If it weren't constant, then it would matter, okay? But we're assuming typically constant density and constant viscosity fluids. So basically then you can look at it indeed as a derivative of momentum, okay? And then you have to have just a different coefficient, which is kinematic viscosity. So that is my momentum perspective. Okay. There's also a resistance perspective, which is useful when we start looking at sort of and relating this to actually electric current transfer. So you can look at the gradient of velocity is the driving force of the transport, and 1 over viscosity is the resistance to it. So then my flux is the driving force divided by a resistance. Okay? So this is basically connecting things to electrical circuits. And that's how you basically arrive to this. This is part of the family of empirical laws. I can kind of connected it to Ohm's law just now. Okay? But we're going to just review these laws. They're all similar in nature, even though they showed up at different times in terms of the how they were developed. So Newton's law is very popular law to relate flux of a quantity and the appropriate gradient in pressure. But these laws are all the guesses that we came up with that work rather well in many situations, but are not necessarily exact. And that's really pointing to that point that Richard Feynman made on scientific method. You observe nature and you guess the simplest linear law, then you compute the consequences, how different it is from nature, and in which cases it's actually very accurate, and in which cases it's not, and then you compare it, and you do that by comparison with experiment. Okay? So another law that is similar is the Fourier's law for heat flux, and again you will have flux of heat, again per area, is proportional to difference in temperature. What's a little nicer and actually easier in heat is that temperature as a field is a scalar field. So this is a simpler thing to compute than actually momentum flux is. But this is also why we're dealing with the momentum flux first, when we are not tired and fresh at the beginning of the semester. Okay? But our momentum is a vector quantity, and velocity as a momentum is a vector quantity. So when it starts changing, that's where you need tensors. This becomes essentially a tensor. Okay? So this K, or the coefficient in this case, is called thermal conductivity. So you have similarities across different types of transport. So if you compare momentum and heat, so momentum looks at the potential difference in velocity, heat, difference in temperature. Driving force is then gradient pressure, heat, gradient in temperature. So driving force is typically looked at as gradient of something. And then flux quantity, how do I refer to it? Shear stress.
Flux, heat flux.
Heat flux. And then my transport coefficient, that is my coefficient of linearity in these two cases. One is viscosity, and the other one is thermal conductivity. So again, stress is a tensor in its full form. We just looked at one component of a tensor so far, which is tau yx. Heat flux is a vector. So that's the different, or mathematical rather, difference. All right. So there's one more law, which is Hooke's law. I'm just going to briefly go over time to just line them up. So Hooke's law can be generalized for solid beam, and we'll look at the shear stresses just in size of these stresses to actually deform a solid have to be orders of magnitude larger than that for a fluid, right? So we're looking at gigapascals here. So basically, the shear modulus is typically in gigapascals, right? So I'm deforming this table, it's just that it's not visible, right? So we have, or rather this way. So shear stress is again force divided by area, and it's shear modulus times so-called shear strain, epsilon xy. It's again a linear law, okay? And most of the time we're solving linear elasticity equations that are generalization of Hooke's law. And then Fick's law is that for diffusion, again I have flux. Okay? Again, we're referring it as J, so this happens because of different concentrations. So difference in concentration will cause a movement of, typically maybe I'm looking at a brine, but I have different concentrations of ions in that brine that will cause diffusion of ions. So in that sense, my phase stays the same, but there's still something moving within. And I'm looking at the difference in concentrations, again, in this direction, and my coefficient now is going to be called diffusivity. Okay? So that's the mass flux. And Darcy's law that I mentioned at the very beginning, again, it's the similar family of linear laws. I have volumetric flux of fluid through a porous medium, so a portion of this tube is blocked, okay, it's a rough core, and geometric description of that core is given by K, description of fluid is given by mu. So I need both because, again, part of my core here is blocked. So that geometric description is summarized in permeability K, but other than that, it's my difference in pressure that drives the flow. So you can see there were times here that are different. So all of these laws basically came up at different times, but now when I look back, They are all this family of laws that connect to flux as a linear function of a gradient in potential. Okay? So in that sense, they're relatively simple laws. All right, I'm going to stop here. So I see you tomorrow, bright and early. Bring some strong coffee.